so far this semester in chapter 1, we talked all about collecting data. And then in chapter 2, we talked about what to do once we have the data. So first, we're going to start by doing what we said was called exploratory data analysis. So we're going to do graphs. We're going to come up with some numerical summaries for the data. And now in chapter 3, and pretty much for the rest of the semester, we're moving on to this idea that, okay, we have this data, and the data came from a sample from the population. So how can we use that sample to draw conclusions about the whole population? So here's another reminder of what the big picture looks like. We have a population. Populations are big, okay? It's the entire group of interest, everybody we want to draw conclusions about. Now, because populations are usually so big, then we're not going to be able to collect the data from everybody in the population. So instead, we're going to take a sample from the population using some kind of sampling method, hopefully a random sampling method. So we take this sample from the population, and then we're going to try to use that sample to draw conclusions about the population. So if you remember, we defined statistical inference already once before, but if you want to write it down again, you're more than welcome to. As a reminder, that statistical inference is basically using sample data to draw conclusions about the entire population. So here's the more formal definition. It says statistical inference is the process of drawing conclusions about the entire population based on the information in a sample. So in chapter 3, we're going to kind of introduce ourselves to statistical inference, and we're going to talk about one of the methods for statistical inference, which is going to be a confidence interval. So in section 3.2, we'll actually start delving into confidence intervals. All right, so before we get going with everything, though, of course, there are more terms that we need to learn. So let's talk about some of the vocabulary that we're going to be using. So the first word is parameter. And a parameter is going to be a number that describes the population. And in order for us to know the value of a parameter, we would actually have to have the values from everybody in the population. So in order to get the actual parameter value, it would have to be computed from all the individuals in the population. So to compute the actual population value, population parameter value. All right, so most of the time, parameters are going to be unknown because, like I said, to know them, you would have to actually have a measurement from everybody in the population. And populations are big typically, so that's going to be really hard, which is why we take the sample and we're going to use statistical inference. There are some occasions when we can know the parameter if it's possible for us to know the value of everybody in the population. And there's certain times when that actually does happen. Like, for example, in the US Census. So when they do the census every 10 years, like 2020 was a census year, then every single household is required by law to fill out the census information. So numbers that come from the census are going to be actual parameters. They're going to be population values because they are computed from everybody in the population. Okay, our next word is statistic. And a statistic is a number that describes the sample. So statistics are much easier to calculate because we're just calculating those from our sample data. Okay, and you notice that we have alliteration going on here. So parameters come from populations and statistics come from samples. So that may be one way that helps you remember the difference between a statistic and a parameter. Now, when we're talking about statistics, statistics come from samples. There's a few other terms that are also used kind of interchangeably with the word statistic or with sample statistic. So I'm just going to put those down here. So one is best estimate. When we talk about the best estimate for the parameter, what we're referring to is the sample statistic. So if my population parameter is the population mean, my best estimate for the population mean would be my sample mean, so the sample statistic. And another way that we refer to it sometimes is a point estimate. Okay, and a point estimate means like a single value estimate rather than an interval estimate, which is what we're going to be talking about in section 3.2. Okay, so thinking about our big picture, again, we have this population, we're taking a sample from the population, then we're going to compute statistics from the sample data, and then we're going to use statistical inference procedures to try to guess what the parameters are. Remember, in real life, most of the time parameters are unknown values because the only way to know them would be to measure everybody in the population. So this is kind of where we're going. So let's think about some parameters and statistics that we're already familiar with. So if we're talking about a mean, then our parameter, the population value, we're going to call that mu. And our statistic, the sample value, we call that x bar. So notice these are all the same when we were talking about notation for a sample, notation for a population. That's basically just what these things are here. So for proportions, our parameter is p and our statistic is p hat. If we're talking about standard deviation, then our parameter is sigma and our statistic is s. And then for correlation, our parameter is rho and our statistic is r. If I'm looking at a problem and I'm trying to figure out what parameter, what statistic is going to be appropriate for this problem, that's where we go back to that chart that we were looking at in chapter 2, where we break it down by how many and what type of variables that we have. So we look at what we measured here. So if my response variable is quantitative, then I'm dealing with means. So I'm just going to put a little notation here. So we're dealing with means when the response variable is quantitative. Okay, we know we're dealing with proportions when the response variable is categorical. All right, standard deviation kind of goes along with the mean a little bit. We're actually going to be focusing mostly on the mean. We will refer to the standard deviation, but we're not going to do a lot of specific inference for the standard deviation. But it is good to be familiar with the symbols because, like I said, it will come up. But when we're thinking about the parameter that we're interested in, the one that we're trying to estimate, it's typically going to be the mean rather than the standard deviation if we have quantitative data. And correlation is what we're going to look at when we have two quantitative variables measured on each individual. All right, so let's look at a couple of examples and see if we can come up with the appropriate parameter or statistic. Okay, so for each of these, we're going to decide if it's a parameter or a statistic, and then we're going to give the correct notation for it. So the first one is the average household income for all houses in the US using data from the US Census. Okay, so first of all, let's decide if this quantity that it's describing here, is it referring to a parameter or a statistic? So first, just tell me parameter or statistic. You could put P or S, that's easier. Okay, so everybody's saying parameter, and you're correct. So we're looking at a parameter. And how do we know that we're looking at a parameter? Because parameters go with everybody in the population, and the data came from the US Census, right? So since we got our data from everybody in the population, then we're dealing with a parameter. Okay, so we know we're dealing with a parameter. So now we have to decide which one. So remember on the previous slide, we had these 4 here. And really we're looking at between 3 to tell you the truth, because like I said, standard deviation's not one that we're typically going to be trying to estimate right off the bat, or that's not going to be our main purpose anyway. So we have to decide between mu, p, and rho. So looking here, do you think that the parameter here should be mu, p, or rho? Yeah, great. We're looking at mu because we're measuring household income. Household income is quantitative. So because we're dealing with a quantitative variable, then we're looking at means, and the population mean is mu. So mu is the population parameter that we're looking at for this one. Let's try another one. Okay, how about the correlation between height and weight for players on the 2014 Brazil World Cup team using data from all 23 players on the roster? So first of all, do you think this is referring to a parameter or a statistic? Good, so this is a parameter because we want to know correlation of height and weight for players on the World Cup team, and we use data from all the players on the World Cup team. So we have information on the whole population. Our population is only 23 people in this case. So we are dealing with a parameter, okay? And what parameter are we looking at here? Are we looking at a mean, a proportion, or correlation? So should it be mu, p, or rho? Rho, exactly. So rho is for correlation. All right, next one. The proportion of people who use an electric toothbrush using data from a sample of 300 adults. So are we talking about a statistic or a parameter here? Statistic, because this one came from a sample. So we're definitely dealing with a statistic. And what's the name of the statistic, or what's the symbol, the notation for the statistic that we're looking at on this one? P-hat, excellent. So we're dealing with a proportion on this one. Good. Okay, so next we're going to look at another example here. You might want to write this down. The wording in this example is very similar to one of your written homework questions, and of course similar to something that you might see on the exam. So this one says, a survey conducted by the Pew Research Center in June 2020 asked 1,015 randomly selected US adults, should children be financially independent from their parents by age 22? Of those surveyed, 650 said yes. So our first question is, what is the population of interest? So remember, the population is everybody we want to draw conclusions about. So what would be the population in this case? Great, so the population is US adults. And sometimes it helps when you think about the population, or when you're trying to think what is the population, if you use the word all, because the population is going to be all of something. So in this case, it's all US adults. So population, all US adults. Okay, so this is our population. So the next thing we want to know is, what is the sample? So if our population was all US adults, what's the sample? So remember, the sample is the subset of the population that we're actually measuring. All right, so in this case, the sample is going to be the 1,015 randomly selected US adults. So these are the ones that responded. We had 1,015 responses to the survey. The 650 is out of the people that responded, the people that said yes to the question. So the sample itself is everybody we asked, not just the people that answered yes to the question. All right, now we're going to get a little bit trickier. Okay, next we want to know the parameter of interest. And when I ask you to tell me the parameter, I want two things. I want the correct notation, and I want a definition in the context of the problem. So correct notation is kind of like what we were doing in the previous problem with those 3 questions that we looked at before. And then we're going to talk about what it means to define that quantity in the context of the problem. Because remember, in statistics, everything is a word problem. So we have a lot of word answers, and we have to put everything in the context of the word problem that we're working on. So let's start with this one. Let's start on the correct notation. So thinking about parameters here. So looking at what I measured, did I measure a categorical variable or did I measure a quantitative variable? Okay, categorical variable, right? So think about the individuals, the US adults. They asked the US adults, should children be financially independent by age 22? Okay, and the people said either yes or no. So that's going to be a categorical kind of variable. So if I'm dealing with a categorical variable, then my parameter, my notation for my parameter is going to be P. Okay, so P is my parameter. That's the notation for my parameter. And now I want to define what P is in the context of this problem. So I'm going to say P equals, and then I'm going to write out exactly what P represents for this problem. and it's probably going to be longer than what you think it would be. Okay, so I write P equals, the first word that should follow the equal sign should be a one-word description of what the symbol was. So if it's P, then it should say P equals proportion, or if it was mu, it should say mu equals mean, or if it was rho, it should say rho equals correlation. Okay, so the first word to follow the equal sign when you're defining the parameter is the one-word description of what the parameter is. So in this case, it's a proportion. Then we have to be more specific. Proportion of what? Okay, well, it's the proportion of all US adults who think children should be financially independent by age 22. Okay, remember that P is our parameter, it's our population value. So it's not going to be the proportion of the 1,015 people that we surveyed, it's the proportion of everybody. So this is how we're going to define our parameter. When I say give me correct notation and define it in the context of the problem, like this is the kind of thing that I'm looking for here. All right, and then the last piece of this is we're going to ask about the sample statistic, and we want to give correct notation and a value. If I look, remember the parameter here, so backing up to parameter, I guess, do I know a value for P, the proportion of all US adults who think children should be financially independent? Do I have any way of knowing the actual numerical value for P here? I don't, right? Because the only way I could know a numerical value for P is if I talked to all US adults. And I'm a US adult. They did not come and ask me this question. So they did not talk to all the US adults, right? You guys, most of you guys are adults. Did they talk to you? Probably not, right? They only talked to 1,015 adults. They didn't talk to everybody. So we do not have a numerical value for the parameter. The statistic, on the other hand, we do have a numerical value for, because we've taken our sample and we can compute the statistic from our sample data. So when we think about our sample statistic, remember that's code word for best estimate for the parameter, then I can give my notation for the statistic and I can give a value for the statistic. So if my parameter was P, what's my statistic going to be? Yeah, P hat. So P goes with P hat. So if parameter is P, my statistic is P hat. Okay, and P hat is a proportion. A proportion is really just a fraction that is turned into a decimal. So we can compute P hat based on our sample data. Told us there was 650 people that thought the kids should be independent by 22 out of 1,015 that were randomly selected or that were participated in our study anyway. So we would take 650 divided by 1015 to give us 0.640 as our P hat estimate. So here, again, I'm asking for correct notation. That's the P hat, and I want to know my value. And if you had to do an intermediate calculation to get that value, it always helps to throw that in there too, especially on your written homework or places where you should be able to show your work. And anytime you're computing something, like our general rule in our class is use 3 decimal places. This is a survey that was done before the last presidential election. So in 2016, then they did a survey where they asked 1,007 likely voters who they plan to vote for in the election. So this is the result of that survey. Survey was done by Quinnipiac, whoever they are, and it was done in mid-October in 2016. And in that poll, we look at the results of that poll, it said that 50% of the people in that survey said that they planned to vote for Clinton. So this 50% came from our sample here, the sample of 1,007 likely voters. So it is a statistic. Now, remember, we said our big picture was to take a sample, look at our sample statistic to draw a conclusion about the population parameter. So if my sample statistic is 0.5, what would my population value be? Well, good question, right? Would I expect that my population value to be exactly the same as my sample value? No, I wouldn't expect my sample to be exactly the same as the population. I expect it to be close. If I took a random sample, then I expect my sample to be representative, but I wouldn't expect it to be exactly the same. And in fact, around this same time frame, there were several different polling organizations that conducted a similar poll where they asked people who they were going to vote for in the election. And here, see, these were all done mid-October. We had actually a bunch of different sample sizes here, a bunch of different polling organizations. And if we look at the Clinton column, you can see these are all the people who said that they planned to vote for Clinton in the last election. And notice that almost all these numbers are different from each other. So we took a bunch of samples, a bunch of random samples, and we got a bunch of different numbers. So when I take a sample, I expect it to be close to the population value, but not exactly the same. And if I was to take another sample, I don't expect that sample to be the same as the first sample, and also probably not the same as the population value. And here I've taken a whole bunch of samples and I got a lot of different numbers for my sample statistic. They're similar to each other, but they're not necessarily the same. Some are the same as each other, but we have kind of a variation in our sample statistic values. So let's think about some of those things right there. All right, so parameters, so remember the parameter is the population value. So a parameter is a fixed number. It is a single fixed value. So these are, I'll just call these key points or key things to consider. How about that? So first thing we're considering is that a parameter is a single fixed value. Okay, so the parameter is something, if somehow we were able to talk to everybody in the whole United States that planned on voting and asked them who they plan to vote for, we would get a number that would be the true percentage of people who plan to vote for Clinton. So we can't measure everybody, so we don't know what that single fixed value is, but it exists. It's just not knowable. Does that make sense? So a parameter is a single fixed value. Sample statistics, on the other hand, are going to vary from sample to sample. All right, so up here on parameters, I said parameters are single fixed values. I'm also going to add that they are typically unknown as well. So, but are usually unknown. Okay, sample statistics are not fixed. They're going to vary depending on the sample that you're looking at, but at least we can calculate them, right? So we can't calculate the parameter. It's a single fixed value. Sample statistics vary, but at least we can compute them. All right, so taking these ideas together, if we can understand how much a sample statistic varies from sample to sample, then we'll be able to figure out how close our sample value is likely to be to the parameter value. And we're going to be able to use that information then to estimate the parameter value. So if we understand how the value of a sample statistic varies from sample to sample, then we can determine how close our sample value is expected to be to the population value. All right, so next we're going to talk about how are we going to be able to understand then how sample statistics vary from sample to sample. And basically, this next thing that we're going to talk about, this is kind of the theory or the foundation for all the different statistical inference methods that we're going to talk about. So if you recall, we just said, okay, we have these sample statistics. They vary from sample to sample. And if we can understand how much they vary or what's going on with the variation, that's going to allow us then to go back and be able to use our sample value to estimate the population value. So in order to understand how much they vary from sample to sample, what we need to do is take lots of samples. If we can take lots and lots of samples, and then from each of those samples, we compute our sample statistic value, and then we look at how much variation there is among all those sample statistic values. That's going to give us the answer. We'll know how much variation there is in the sample statistic, and then we'll be able to use that information to draw conclusions about the population value. So this idea of taking lots and lots of samples and then looking at the distribution of all the sample statistics from all those many samples that we're collecting is called a sampling distribution. So we're looking at a sampling distribution. Okay, and a sampling distribution is the distribution of sample statistics. So this is the definition. So it's a distribution of sample statistics computed for different samples of the same size from the same population. Okay, so again, we're going to take lots and lots of samples. From each of those samples, we're going to calculate our sample statistic, whether that be X bar or P hat or R, one of those kind of things. So we're going to take all these samples. From each of our samples, we're going to calculate, say, X bar. Then we're going to look at all those X bar values from all those different samples, and we're going to see how they're distributed and how the sample mean behaves, or the sample proportion, or the sample correlation. It works for all of them. So by doing this, the sampling distribution is going to show us how sample statistic varies from sample to sample. All right, so we are going to look at a little example to try to kind of help us understand what a sampling distribution is and what a sampling distribution does, and see if we can figure out some of the characteristics of a sampling distribution. So I'm going to be doing this mostly inside of StatKey, and if you want, you can pull it up and do it yourself inside of StatKey too, so you can kind of learn which buttons to push and everything. So that's an option, or you can watch me doing it, and then if you get to the homework and you're like, hey, I don't remember how to make the sampling distributions, then you could go back and watch this video and hopefully figure it out. I've also posted another video already inside of Blackboard that just looks specifically at creating sampling distributions inside of StatKey. What I'm going to do, okay, the idea of a sampling distribution is that we have a population and we're going to take several samples from that population. So to start with, I need a population. I need something where I can actually have the values of everybody in the population. And so I'm going to use a data set that is from your textbook. It's called the US States data set. I'm going to flip over to StatKey, and I'll show you how we can get that data set. So again, if you want to do this also while I'm doing it, that's great. So in order to find the data from our textbook, one way of getting there is if I click on the title of our textbook inside of StatKey, and then click over here on data sets, it pulls up that data set list. So if the data set I'm going to use is called US States. So it's all the way down here at the bottom. And I'm going to download the CSV file because then I can just easily upload that into StatKey. So, and I've actually already downloaded it on my computer, but if on your computer, if you're doing this, then you should just click on where it says CSV, and that should let you download that data file to your computer. Once you have the data set downloaded, then we're going to go back to StatKey. So if I just scroll back up, I can click over on StatKey on the side. And before I start thinking about taking samples and all that kind of stuff, first thing I want to do is I want to examine my population. I just want to see, what does the population look like? So this is an instance when I actually have measurements from the whole population. And what we're going to be looking at, there's lots of variables in this US States data set, but the variable that we're going to look at is called the physical activity. And what it is it's the proportion of people in the state who exercise for at least 30 minutes a day, 5 days a week. So basically a minimum of 150 minutes in a week. So it's the proportion of people in the state that do that. So from each state, I have this proportion number. So it's a quantitative variable because I have a number from each state, and it would make sense to talk about the average proportion in this case. So I'm going to look under one quantitative variable to just first examine the population itself. So I'm just going to look and see what my population looks like first, and then we're going to talk about taking samples from it. So I need to get my data file in here first. So I click on upload file, and I have to find it. In mine, it was in my downloads folder. There it is. Then it's going to ask you what variable you want to look at, and we're looking at the physical activity variable. So you might have to scroll over and then highlight the column that says physical activity if you're doing this along with me. So upload data, choose the US states data set, and then you're going to choose the physical activity variable. All right, so here is what my population looks like. So I've got a dot plot of my population, and I have all the summary values from my population. So if you look over on the side here, you can see that the sample size is 50. This is actually my population, so this would be my population size. So what does one dot in this dot plot represent? Where did the number come from for that one dot? So each dot in here represents what? Like, what are the cases, in other words, in this population? Yeah, the states. So here, if I click on change columns, I can bring back up the data set here. Okay, look, I have a measurement from every state here. So the states are my cases in this case, and I have a measurement from every state. That's what makes it the population, because there's 50 states and I have measurements from all 50 states. So each dot in this dot plot represents an individual in my population, which would be a state. So each dot is one state, okay? I can look at the mean of all the states. So the mean of my population then is 50.734. So write that down on your paper. Write down, okay, population is all 50 states. Write down that one dot in my population graph represents one state or one individual, in other words. And then write down that the mean of the population in this case is 50.734. And because I'm talking about the population, what kind of notation would I use if I was using notation for that mean? Mu, exactly. Okay, so mu is equal to 50.734. All right, and go ahead and write down the standard deviation as well. And this standard deviation came from my population. So what's the notation for population standard deviation? Is sigma, right? Sigma. So remember, sigma is the little thing that looks like a kind of like an O that's wearing a little baseball cap, like it has like a little thing that sticks out from its head. So write down sigma equals 5.510. All right, and let's look at the shape of this population here. We can look at the dot plot because there's only 50 dots. It's kind of a lame looking dot plot, but I think the histogram is a lot more interesting to look at in this case. And if I look at this histogram here, what kind of shape does this population have? Okay, it looks bell-shaped symmetric, right? So this is a kind of a nice bell-shaped symmetric graph, and we could mess with the buckets over here, but pretty much no matter how you look at it, it's a bell-shaped symmetric distribution. It looks lovely. Okay, this is my population. So now what I'm going to do is I'm going to see if I could create a sampling distribution. So first I'm going to show you how this would be, like the process that we're going to go through. And then I'm going to show you the super easy way to do it in StatKey. Okay, so I'm going to take a sample from this population. So my population has 50 states. I'm going to take a sample of 4 states. And there's this cool website here. It's a random list. And if you go there, you can get it to randomly select all kinds of different things. It's kind of fun. But I can have it randomly choose states. And if I go down here, I can tell it, hey, I want you to randomly choose 4 states. So I'm going to take a random sample of 4 states. All I have to do is click on this rerun. Look at that. I've got my 4 states right there. So this is, I just took a random sample. I used a random number generator to select 4 of the US states. So on your paper, write down the names of these 4 states. I'm going to write them down too. Okay, so if you got all those state names written down, now what I'm going to do is I'm going to come back here in StatKey. And if I click on the change columns button, it'll just bring back up the data set here. And I'm going to find the physical activity value for these 4 states, for Oklahoma, Iowa, Delaware, and Idaho. No, not Idaho, Ohio. Ohio. So starting with Oklahoma. Okay, so Oklahoma here is the second one on my screen. And now I'm going to go over and find the physical activity variable here. So for Oklahoma, the value for physical activity is 43.9. So next to Oklahoma on my paper, I am writing 43.9. Okay, so I've got Oklahoma. Now I'm going to do the same thing for Iowa. So scroll up here to Iowa. There it is. I've got Iowa at the top of my screen. That'll make it easier to see. And then I'm going to go over to physical activity. And for physical activity for Iowa, it's 47. So I put down 47 on my paper next to Iowa. All right, then I'm going to look for Delaware. Okay, so I've made Delaware at the top, easier to find. And I'm going to scroll over here to physical activity. So physical activity for Delaware is 49.7. Okay, so next to Delaware on my paper, I wrote 49.7. And then finally, I'm going to look at Ohio. Found Ohio there, scroll over to physical activity. Ohio is 49.5. Okay, so I wrote that down next to Ohio on my paper. So now I have all 4 of my states that were randomly selected, and see, my paper's like my doodle paper over here. So, and I've written down their physical activity values. Okay, these are the values in my sample. Okay, so now I've collected my sample. The next thing I'm going to do is I'm going to compute the sample statistic. Okay, so my sample statistic is X bar. So in order to find X bar for these values that we just wrote down, then I'm just going to add them up and divide by 4. So everybody do that on your calculator. See if you can tell me what X bar that we get. All right, sweet. Looks like you guys are all getting the same thing that I did. So I ended up with 190.1 over 4, and that equaled 47.525. Okay, so 47.525, that is one of the possible sample means that I could get if I take a random sample of 4 states from this population. So this would be the first piece of my sampling distribution. I've taken 1 sample so far. Now guess what we would do? We would do it again, okay? In fact, guess how many times that we're gonna do this? Like 1,000, or maybe 3,000 times, or 5,000 times. So can you see that doing this by hand, the way that we did it, is a little bit on the tedious side and would probably take us until next year. So the good news is that StatKey has a way of doing this just like blink your eyes and it's done. So I'm going to show you how we're actually going to make StatKey be the one to take all of our samples. But I want you to understand where the numbers are coming from in all the samples that StatKey is doing. And StatKey is basically doing this. It's coming up with a random sample of 4 states, finding their physical activity values, and then computing the mean from that sample. And it's going to do that thousands of times for us. Okay, so in StatKey, go back to the main StatKey homepage. And now you're going to come down kind of in the middle-ish section. There's something that says sampling distributions, and there's 2 options. We can do sampling distribution for a mean, and we can do one for a proportion. So right now we're looking at means with our states data. So we're going to click on mean. So go to sampling distributions and then choose mean. All right, and the first thing I need to do is I need to tell it what population to take the samples from. And we've been using that US states data. So if you already put it in to look at before, then when you click on the drop-down box, you'll notice down at the bottom, it'll say US states CSV. So it kind of keeps the last thing that you've uploaded in that session anyway, in its memory, which is handy. So you can click on it that way. If you don't have it in that menu, then you would have to go to the upload file and put in the US states data and choose the physical activity variable, just like we did before. All right, so now I've got my physical. I've told it, hey, I want you to use this physical activity data as my population. And notice over here on the right-hand corner of your screen, then it actually gives us all this great information about the population. So it tells us that there was 50 individuals, or 50 states in this case, in our population. Okay, so it tells us the mean of our population. So remember when you wrote down the population mean, it was 50.734. Look, here it is right here. So it's telling us that. Tells us the median even. We didn't even write that one down. Tells us the standard deviation, 5.51. And it gives us this cute little dot plot of the population. So this stuff in the upper right-hand corner over here is always going to display the information about the population. Now we want to start taking samples from the population to create our sampling distribution. So up here where it says choose samples of size, we're going to change that to 4 because we're just taking samples of size 4. Okay, once I've changed that, now I'm going to click on generate one sample. So I'm having it just make one sample, just like we did here. So I've got my one sample here. Down in the lower right-hand corner over here, it has the information for that one sample. So, and if I click on show data table, it'll show me exactly which values were included in that one sample. So I don't have, it doesn't have the states labeled here, but these were the 4 values that came from the 4 random states that it chose for this one sample mean that it's computed. And it gives me a dot plot of that. It tells me the mean of that sample and all that other good stuff over there. So now what I want to do, like we said before, is we want to do this lots and lots of times. So you can click that generate one sample button, and you can see that every time it's taking another random sample of 4 states, calculating the sample mean, okay, and drawing a dot on the dot plot. So the clicking one sample will slowly build up your sampling distribution here. But you notice there's this option to generate 1,000 samples. So this is how we're going to get places quick. So on your homework, especially your Wiley Plus homework, you're going to want to generate a whole bunch of samples, like minimum of 3,000, probably even more, like 5,000 or even 10,000. All right. Now, thinking about this one here, and actually I'm going to go back to only having 1,000. So I'm going to reset and just click on 1,000. And if you roll over any of these, notice that the information in the data section over here changes depending on which dot you're rolling over. So it's going to show you the information behind each of these different dots. So what does one dot on this dot plot represent? So we said in our population, one dot was one individual, but in a sampling distribution, one dot is one sample mean. So it's one sample statistic. In this case, it's going to be one sample mean from a sample of 4 states. So one dot, you might write that down, write down sampling distribution, and then write, one dot equals one sample mean in this case. All right, so let's see if we can figure out some characteristics of this sampling distribution here. Okay, so I started with 1,000. I'm going to put a few more 1,000 in there now because I don't need to see the individual dots. They kind of get muddled together when you have a lot of dots on there. All right, and if I look in the upper right-hand corner of this plot, it's going to give me the information related to this actual graph here. So this is telling me that there's 9,000 dots here. In other words, I took 9,000 samples and I plotted 9,000 sample means in this case. It's going to tell me the mean of all those dots, of all those sample means. So this is the mean of my sampling distribution. And then it's also going to tell me the standard deviation of the sampling distribution, which we're going to call the standard error. So we have a special name for the standard deviation of the sampling distribution, which is the standard error. And we'll write that down in just a second. So, but I just want you to look at this here. What do you notice about the mean of the sampling distribution over here? and the mean of the population? Do they look similar or not similar? Like, do they look same or different, basically? Pretty close, very similar, right? They might not be exactly the same, because in order for them to be exactly the same, we would have had to look at every possible sample you could take, and that would be a lot, like more than even than 10,000. It would probably be millions of samples. But it's going to be pretty close. And you notice, even if I reset the plot and I do it again, then I'm going to end up with a value that is very close to the population mean. So the center, or the mean, of my sampling distribution should be pretty much the same as, or very similar to, the mean of the population. So that's a good thing. Okay, now let's look at the standard deviation of my population versus the standard deviation of my sampling distribution. How do those numbers compare? Are they same or different? Yeah, they're not close. And what do you notice? Which one's lower? The sampling distribution is going to have a smaller amount of variation. So the means are going to be the same or pretty close for the sampling distribution, but the standard deviation of the sampling distribution is always going to be less than the standard deviation of the population. And that's because means vary less than individuals. All right, so I want to go back to the presentation and write down some of this stuff, and then we're going to look at just a couple more things here. So, okay, so before we had sampling distribution up here. So these are some characteristics of the sampling distribution. And really here, just going back to my graph here, I'm looking at a dot plot here, right? And what are the three main things that we look for on a dot plot? Remember our little acronym kind of has 3.5 things in the acronym. Oops, I went away and then it erased everything that I wrote. Yeah, SOX, right? We look for shape, center, spread. So that's basically the three characteristics that I want to talk about for this sampling distribution. We're going to talk about shape, center, and spread. Okay, so first, let's talk about shape. If I leave this page, it'll erase everything I have. So I'm not going to go back to my other screen. But did anybody notice what the shape of my sampling distribution was? It was bell-shaped. And we're going to find that sampling distributions in general tend to be bell-shaped and symmetric if our population was bell-shaped or if our sample size was large. So our sample size was only a sample size of 4, so it wasn't large, but our population, remember the original population was symmetric. So our sampling distribution is also going to be symmetric and bell-shaped. Okay, next thing, the center. Okay, and we saw that the center of the sampling distribution is the same as the center of the population. So basically, if the sample is randomly selected, the sampling distribution will be centered on the population parameter. So the sampling distribution will be centered on the population parameter. So in other words, the mean of one will be pretty much equal to the mean of the other one. So that's good. That means that when we take a sample, we're just as likely to get a value that is above the parameter as we are to get one that's below the parameter. So that means that our statistic is unbiased. Okay, and then as far as spread or variability, we saw that the spread was less, and we decided to give a special name to the variation of a sampling distribution. We're going to call it the standard error. And we even have an acronym for standard error. It's SE. Okay, so the standard error is the standard deviation of the sample statistic. And so it's basically just calculated by finding the standard deviation of the sampling distribution. I'll write that too, although it might seem kind of obvious. So standard deviation of the sampling distribution. That's how we can calculate it. And if our sampling distribution is bell-shaped symmetric, how we have a special way that we can estimate standard deviation from bell-shaped symmetric distributions. If we have a graph, for example, like a dot plot or a histogram, and the distribution is bell-shaped symmetric, what could I use to estimate the standard deviation? Yes, the 95% rule. A couple more things I'm going to point out. All right, so first of all, if you back up to where we talked about the center of the sampling distribution, you'll notice that we said if the sample is randomly selected, the sampling distribution will be centered on the population parameter. So the sampling distribution is only going to be centered on the population parameter if the sample is randomly selected. So if we use a method that is not random to select our sample, then our sampling distribution will not be centered on the population parameter. So basically our sample is going to be useless to us. So here is an example. So remember when we did that exercise with the quotes from The Princess Bride, and we everybody took a sample in their own way of 5 words, and then they looked at the length of each word, and you computed the average length for your sample of 5 words, and then you put your X. In our case, we did stars. I couldn't get a picture of both graphs together from our class because of the virtual way that we had to do it. So this is actually from a previous semester, but ours looked similar to this, okay? And you didn't know it at the time, but you were creating a sampling distribution. So each of those stars that you put on the graph, each of the X's on here represents a sample mean computed from different samples. And we saw that when we did not use a random method, then our graph was not centered on the true population value. Remember, the true average was 3.6, and you can see our plot is not even close to that when we didn't use a random method. Now, when we did use a random method, then the values were actually pretty close to being centered on the true population values. You can kind of see from here. This one's a little heavy on this right side, but it's only based on a few values as well. So you can see that when we use a random method, then the distribution will be centered on the population value. Okay, so next I want to go back and look and see what happens to our sampling distribution if we change the sample size. So we were taking a sample of 4 states at a time, but what if I took a sample of 10 states at a time or 15 states at a time? Like, how does that affect what my sampling distribution looks like? So I'm going to go back in to stat key here, and we're going to see if we can figure that out in the last couple of minutes that we have. All right, so the sample size up here can be changed just by clicking on it. Okay, and something that I want to point out is that the sample size is different from the number of samples. So in this plot right here, my sample size was 4, but the number of samples was 8,000. The sample size refers to how many states were randomly selected, and I computed the mean from that number. So each of the dots on here, can't see the dots anymore, they're all blended together, okay, but each dot is a mean calculated from 4 states. So that's where sample size is, it's the mean from 4 states. This number of samples is the number of times that I take a sample of size 4 and compute the mean. So you see the difference there? Is the distinction is important. All right, so we saw here sample of size 4. I had a mean that was very similar to the population mean, and my standard error in this case was 2.641. So remember that number, or even write it down if you want to. That was when my sample size was 4. Let's look and see what would happen if my sample size was 10. So I'm going to change my sample size to 10, and I'm going to go ahead right away and generate, I'll just go for 3,000 samples. That sounds good. Okay, I can look at my mean of my sampling distribution over here and the mean of the population. They're still pretty similar. What happened to the standard error, the standard deviation of that sampling distribution? It went down, right? So it was 2.6 something before. Now it's at 1.537. Okay. And if I roll over these dots, you can see in the lower right-hand corner that now these means are based on samples of size 10 rather than size 4. So there was 10 numbers that were averaged together to get each one of these dots rather than just 4. And I'm going to change this to 15, see what happens there. I'll create a few thousand samples there. Okay, and what happened to my standard error? It went down even more. So the bigger my sample size, the smaller my standard error. So that just means that I'm going to be more likely to get a sample mean value that is closer to the population value, which makes sense. You would think that if you took a bigger sample, that should be better. That should get you a value that's closer to the actual population value. And it does. Like, it increases your odds of getting a sample value that is closer to the population value. All right, so sample size matters. The variability of the sample statistic decreases as the sample size increases. So if the sample size increases, the standard error, okay, that's what the variability of the sample statistic is. And maybe you even just want to write that. So I might be able to just write that underneath here. So as sample size increases, the standard error SE decreases. All right, so that's going to make it more likely that we're going to get a value that's close to the parameter, which is good because that's exactly what we want. All right, and if I look back here, back at my graph, and maybe I should do this here. I'm going to go back and create one with 4 again real quick. Okay, so remember, these are kind of showing us like all the possible values that we could get for X bar. Now I've changed the sample size to 4. So if I take a sample of size 4, these are the possible values that we can get. So if I look at this graph, okay, look, there's lots of sample means that are in here around between like 47 and 55. There's a whole bunch of them. But if I look at some values out here, like how about 45? Okay, if I look at 45, I could get a sample mean of 45, but it's not very likely. There's not very many values out here and beyond that. So it's unlikely I would get one beyond 45, but it's really likely that I would get one at, say, 47. Okay, so remember these numbers down here. So 45 was somewhat unlikely, 47 was pretty likely that we would get that. Now, if I change this to, say, 15 and regenerate it. All right, so one of the numbers that we looked at isn't even on here. So it would be like we wouldn't even get a sample mean that was as low as that first number we were talking about. And if I look at 47.5, that was really likely when I had a sample of size 4. Now it's not very likely at all when I have a sample of size 15. So if we could somehow see these on the same scale, you would see how we're having a bigger sample size makes it more likely that we're going to get a value that is close to the parameter value. All right, sampling distributions can be really tough to kind of wrap your brain around. So if you kind of feel like deer in headlights or like your brain's going to explode as we kind of try to talk about this, then it's okay. I do recommend really trying to understand it though, because sampling distributions are the foundation of everything else we're going to talk about this semester. So it's possible to like go through the motions on the things that we're going to start learning about, but unless you really understand what a sampling distribution is, you're going to have a hard time understanding why and how everything works as we kind of move forward. So I do recommend just taking some time, like read the textbook on this. There's a Khan Academy video that's okay that talks about sampling distributions that might be helpful. But just trying to get some different ways of it being explained to you so you kind of understand this is what a sampling distribution is, and that will really help moving forward. And definitely as you do your homework and things like that, it will help too. But if you don't get it today, right this second, then don't worry, you're not alone. I bet if we took a poll, at least 80 to 90%, maybe 95, maybe 100% of the class would be like, yeah, I have no idea what she's talking about today. It sounded like she was speaking a foreign language.